Whoa, baby, what the cockadoo? What is going on?
Get on the other side of the building.
I'm not talking talk about enough time, about the You have trouble with the poppers, gentlemen? They have a lot of us. Remember, you got to ask the second number one. All right. How you doing all today? All right, you're going to read 7th out, right? Yep. I'm actually going to leave your class for a little bit because I have to go to the junior meeting. I guess I'm your sponsor. So don't, Mr. Slard will peek in with don't hurt his. At any rate, so the idea for today is that we're going to go over limits like crazy. Actually, we'll do a warm-up, then go over limits like crazy, and then hopefully we'll have time to go over that homework some more, but if not, in 7th hour through you. All right? Ready for the day, Chef? You'll need that green sheet on the back counter eventually, so if you didn't pick it up on the way in, pick it up now. Please come get it.
Well, of course.
Hey, now this warm-up is actually not on the green sheet. I would like you just to think it over, jot down your answers in the corner of the paper or whatever, or just in your mind, keep track of your answers. There are 3 columns there that were a little like ones on the review that I'd like you to tackle. Can you see that okay?
Yeah.
All right. So think about those, talk them over. I don't ask that you do them right. I'll ask that you try. Okay, so as long as you're not sitting there thinking about your girlfriend, waiting for somebody to do it for you, we're all good. Not necessarily sure so much as it takes to get the answer. These would be multiple choice type questions. So just so you remember your answer when it comes in. Let me take some attendance. Sarah, Alex, here. Kyle, here. Hunter, here. Cole, here. Sabrina, here. Charles, here. Jet, here. Matt, here. Sebastian, you're here. It's up to you. Where did I leave off? Evan. Here. Ethan. Here. Alexis. Here. Where's Alexis? So, my nephew tells me you say I'm a big jerk who gives too much homework. Is that right?
Yep.
Okay. Good to know. I have ears everywhere. Alexis, thank you for that. Christy. Here. Antonio. Here. CJ. Here. Kenny. Here. Michaela.
Here.
Oligny. Yeah. Do these glasses make my eyes like really big? They're reading. All right, just curious. Charity. The other Michaela. How about if I just call you Porter? Sounds good. Luke. Here. Rebecca.
Here.
So lovely to see you all today. Another minute or ready to go? Okay. Oh, sorry. You're right. This is undefined at 2, yes? So this should have been, you're absolutely right. Good point, right away. I wouldn't change something. So if you're thinking that's a trick question, G is not defined, that would be true. It's actually not possible, but now it is possible. Thank you, you're right. I had 3 or 4 questions on these kind of function problems yesterday, which means that we need to practice it a little more. You need to really be fluent with these before you get into calculus with these. So we're giving you a little function practice, numerical, analytical, and graphical. What's the one I'm not giving you practice on? Verb. That's why you're doing this. Oh, that's bad. My bad. That's not the button I hit. Here to hit. Yes. What do I do? Yes. There's no yes. Okay, there you go. I need to freeze. Is what I want to freeze. Okay, sorry. One more minute. We'll roll. Ready? Sounds like we're ready. What do you say for the first one? 21. Do we all concur? Any questions about where 21 is coming from? Okay. Is that composition of functions or multiplication of functions? Multiplication, right? So we need to know the products. What does f of 2 mean? If you're going to explain that to your little brother or sister, what does it mean? When x is 2, the outcome or the y is whatever, right? So looking at f, when x is 2 into the rule, what do we get out? 3. So that would be 3, and we're going to multiply it by the next outcome. That also means when x is negative 2, what comes out? Well, here's g. That's the information about g. When x is negative 2, the outcome is 7. That's where 21 is coming from. Cool? All right, this one. Multiplication of functions kind of feels like it, but is it? No, that's composition of functions or h within g, right? So you work inside out. You need to first find this. H of 6 means, here's h. When x is 6, what is y? And it looks like, although it's hard to say, let's guess at 0. Okay? Now, that is just that I've done, so now that gets replaced by 0. Now, a second step then is, what is g at 0? Here's g. X is 0. The outcome is 4. Is that what you got? Yes? Thumbs up or thumbs down, people? Okay, cool. C is the hardest one. What'd you get for an answer? -5. Throw it out. It's calculus. It's okay to be wrong. It's very free. -5 is the only answer. Okay. Let's see if we all agree. G inverse at 7. That to me is a bummer about notation. Somebody along the line screwed up. When you put that notation on a number, what does it mean? It's reciprocal, okay? On a number, that is an exponent, that's reciprocal, it's 1/2. However, on a function, that notation doesn't mean reciprocal. It means inverse, it's inverse, okay? And that's goofy. So you might say, well, what notation do you use for reciprocal? Well, if I want reciprocal, I'll write it that way. Okay, this notation does not mean reciprocal, it means inverse. Understood? Okay, so inverse means the old switcheroo of the x and y. So if I do g inverse of 7, that means the y is 7. What's the x? Well, the y is 7, the x must be -2. All right. Now maybe this is the part that tripped you up. Maybe you got that part. There's also a second hard part, is this piecewise function's a little weird. At -2, there's the x value. Do I report -3 or -5? It is -5, okay? It's where the point is. Now, the limit would be different. The limit would be -3, and we'll talk about -3, and we'll talk about that today. But the answer is indeed -5. You are correct. How'd that go? Good or more practice? We're going to need to practice that more.
Yes.
That was an or statement, for Pete's sake. How do you answer an or statement with a yes? That's ridiculous. Okay, let's move on to the notes, shall we? Here we go. All right. So like most textbooks, limits are the starting point. Without limits, there is no calculus. It's sometimes said that calculus is algebra with limits. Okay? Now, that doesn't mean there's limitations to algebra. It means you're taking algebra and giving it some kind of superpower of limits. That's where calculus was invented, all right? The infinitesimally small and the infinitesimally large is what calculus is all about. And you can't really go to infinity, you can only approach infinity. You can't get zero in some cases, especially if there's a denominator. You can just get close to zero. That's why limits. You've got to be very fluent with these. And if we got to go over and over this, we will. But hopefully, this will be a really good reference. This would be about 3 problem sets in the book. Set 14, 18, 14, 16, something, 17, like that. So I'm going to cover a lot of ground. It's crucial that you, if you don't understand, you ask me questions, all right? Okay, so here we go. The limit of a function is just what number, and it's a number, okay, what number the function or the rule approaches as x gets closer and closer to whatever they say. So it's basically like as x goes to wherever they tell you to, where does the y go to? All right, it's all about action, going, going, going. So take a look at this graph here, which we'll call f. I didn't label it, but that's f of x, all right? When they give you this little statement, obviously lim is short for limit, they're telling you that x is going to -5. So we can find -5 on the graph. Go along the axis to x of -5, and that's where I'm looking at. Now, when I go up to -5, I could either see a dot or a curve and a curve, all right? Now, I need to get a little more specific. They are asking, this little negative above, or just to the right of that 5, means approach it from the negative side, or from the left side. So if I go to -5, and maybe a few x's to the left of that, for the curve, that would be on this part of the curve, right? It wouldn't be the dot, and it wouldn't be that curve. It would be this curve, right? You with me? Now, if x gets closer and closer to -5, I'm going that way along the curve. Now, I'm not asking you to do a table, but if I did a table, a numerical, the y's might be, as I do that, the y's might be something like 2.7, 2.8, 2.9. If the y's are going to 2.7, 2.8, 2.9, 2.99, what are the y's going to? 3. You'd say that trend or that approach seems to be 3. Well, that's the limit then. F of x or y is approaching a value of 3. Again, if you look at along the curve and then say, all right, what's the y associated with that? They're getting closer to 3, right? Now, and it's pretty easy so far, I hope? Yes? Okay, good deal. All right, so getting then gradually harder. Would you do the next one, please? Example 2. What about the limit as x goes to -5? I think that says -5, doesn't it? From the positive side? Does it say positive side? Okay, this is not real clear. Okay, so what do you say? It's 3 also. Okay, cool. The y values are approaching 3 on that right-hand side of the curve. All right, now here's the first where it starts to get a little more theoretical, right? If the left-hand limit, this from the negative side is the left-hand limit, and the right-hand limit from the positive side is the right-hand limit. If those two limits are equal, then the limit, or the general limit, is that same number. So you can see that in this case, it's just -5. As x goes to -5, not from the left, not from the right, just -5. What's the limit? And it's 3. Okay. Now that only is true if the left hand and right hand are the same. Okay. There should be no confusion. It's pretty clear from the left is 3, from the right is 3. Must be 3. Over here, though, example 4. Take a look at this. As you go to, sorry, I'm a little over the place, so I'm going over to example 4 here. With me? When I go to 3, from the left, what's the limit? What are the y's approach as I get closer to 3 from the left? 1. Just trace back over to the y value. And they're approaching 1 as I go along the curve from the left. As I go from the right, what are the y values approaching? -1, okay? So then what's the limit? Is it 1 or negative? It does not exist, okay? So if the case is that they're not the same, if you don't know what to say, that's because the limit, the single number, doesn't exist, all right? There is not a single number that is the limit. Now you're going to say, does not exist. This is not just my little preference. Everybody, at least in America over, says DNE, okay? That's fine to abbreviate it that way, including on the AP exam. You may write DNE. However, this is where, as your teacher, I get a little picky, kind of again at the college level. I am a little picky in that I require you to justify why you say that. Okay? So when you say DNE, I require you to answer why it DNE. A limit only exists if the left-hand and right-hand limits are the same. This doesn't exist because the left-hand and right-hand limits are different. So I'm going to say DNE because, that also is okay. Now you can say this one of two ways, in plain old English, verbally, or analytically. If you did this in plain old English or verbal, you'd say it's because the left-hand limit now I said with evidence. It's not okay to just say the left-hand and right-hand are different, period. You must give evidence. The left-hand limit, which is, what's the left-hand limit, please? 1, which equals 1, is not equal to the right-hand limit, which again, you must say evidence. What's the right-hand limit? Equals -1. Okay? Now, symbols were invented to save you time. That's verbal and it's great. And for a lot of people, especially, AP Englishy people, they like that. It works for them. Me, I'm not a symbol guy. I want to save time. All right? So I could say the same thing in symbols. In what feels like a really run-on-y kind of way, but you'll see it's all good. Okay? It would go something like this. The left-hand limit in symbols would be the limit as x approaches 3 from the left. And that's where that little negative after the 3 comes from. This is going to be where you make me crazy for about a month. You never write a limit statement without an argument. Okay? So it's the limit of what? F. Okay? Now, I'm not picky about the argument. If you say of x or not, most teachers are cool with that, okay? But no teacher is cool with just limit with nothing in it. That will make me nuts, and you and I are going to have to step outside if you do it for much longer, okay? So the limit, that means to fight, by the way. The limit as x goes to 3 from the left, which is -1, is not equal to the limit as x goes to 3 from the right of f, which is equal to -1, okay? Now, I prefer symbols, but those two things mean exactly the same thing. What you must give is, first of all, the whole justification, and second, the evidence. You must cite evidence. You cannot just say they're not equal, period. You must say, here are the limits, they're not equal. Okay? Any questions? That's usually a part that people have a little getting used to. Depending on your teacher, if they're a total softy, pansy, then they might be okay with you not justifying it like that, but your teacher's not a softy pansy, all right? So what is this about here? Okay, would you take a look at -3 then? Now, coming back to here, example 5, we're approaching -3 from the left. So, find -3, go a little below it, then go up to the curve and approach. And then tell me, what are the y values approaching? What are they approaching? Infinity. True. Okay, like all numbers, if you don't put a positive in front of it, it's implied positive. Okay, so then you could put positive infinity, but you could just leave it like that. What about from the right? Approaching -3 from the right. That's what that means. -3 from the positive side of the number line, which is what? Infinity. Okay, here's another kind of iffy point here. So what about the limit at -3? It's infinity. So you could go two ways here. Do the left-hand, right-hand limits agree? They do, okay? And so that means the limit is whatever they approach, infinity. Now, look back at the definition of a limit. The limit of a function is what number the function approaches. Is infinity a number? It is not. Okay, so a lot of textbooks will argue that you should say DNE there because it doesn't satisfy the definition of a limit. That is not a number. Both are pretty common. It's really your teacher's perspective. I would prefer DNE, or sorry, I would prefer infinity just for purposes of her class and folks we'll talk about. So would you please, in my class, answer infinity? Okay. Now, the reason I even give you both is because in multiple choice, sometimes you'll see infinity is not a choice and D and E is. And so you need to be aware that it could be the case. Cool? Okay, give example A to go. See what you think there. Talk it over, and we'll move on to from graphical to analytical. Okay, what do you say? It's 1. Okay. Now, should we go over that? Are we good, or are you understand? Basically, do the inside. As you can't, I know I want to square root it, but you first have to say, what does f do? I can't square root something I don't know. So I have to square root, I have to first find f. What is f doing? Well, the y values are approaching 1. If you then square root all those values, that would also be 1. Understood? Any questions so far? Okay, great. Moving on. Analytical is probably half to more of the problems in a normal calculus class. You usually do limits analytically. The reason is because the definition of the derivative is an analytical process, and so you really need to be good with these. Okay, so the first thing is I want to know, when you do analytical, you want to know what this expression is approaching. As x gets closer and closer to 2, what does that total thing outcome approach? Well, in most cases, what it approaches and what it actually is are the same thing. So rather than approach 2, your first goal is to see, can I just go straight to 2? That's called direct substitution. If you direct substitute 2 in, what is 2 squared minus 9? -5. Okay, now that, I'm going to write the work there, so these are valuable notes, but it's basically just what it approaches and what it is, or one and the same. That's a really soft, that's a delightful case. Mostly in the definition of the derivative, that doesn't happen, but well, that's the first thing you check to see if you can do that. With that in mind, then, what's example 10's answer, please? Clicker. 0. Thank you. Okay, that is direct substitution, 0 over whatever. I don't care. It's not 0. That's the only thing I care about. It's not 0 over 0. So 0 over a non-0 is 0. All right. Now, when things get iffy, okay, when direct substitution fails, you always look to direct substitute. But if direct sub doesn't work, and in calculus, the most common reason is because you get 0 over 0. That's what happens when you do a definition of a derivative. You'll always get 0 over 0. If there's just going to be a small change in y, change it, you'll get there later. Okay, so at any rate, if that's the case, then direct sub fails. 0 over 0 is a hole in the graph. It's indeterminate, so we need to do something. If you can play with the function a little algebraically, then you can do that. What can I do algebraically? Do you agree that I get 0 over 0 if I try to put 2 in? Okay, so direct substitution fails. So you might try a little algebra. What could I do there? I could factor the numerator. The limit as x goes to 2 of x plus 2 over x minus 2 is x minus 2 over x minus 2. The x minus 2 drops away. Now, once that factors out or divides out, the 0 over 0 divides out. And now I can put 2 in. What do I get when I put 2 into the rest? 4. Okay? So your goal is to do some algebra so the 0 over 0 problem dumps away and you can direct substitute after. Look over here, please. This also is makes me your starting calculus teacher crazy. Look at your work. Did you write this in the second step, or did you just say, well, in fact, I forget the limit thing. I don't even know what it means. This must be there. Until you evaluate the limit, it's there. Write it. Keep writing the limit statement until you have actually evaluated the limit. Okay? When I go to factor, I haven't put 2 in yet. It's still waiting to be put in. This is just me trying to help myself so I can put it in later. It hasn't been done yet. That must be there until you can get to the point where the 2 goes in. Write it. All right. Other algebra you can do is rationalizing the denominator or numerator. So for example, you could multiply this. Do you agree this is 0 over 0 if you try to direct substitute? Okay. So you can multiply top and bottom by, oops, let me write that over the side so I can do this. Okay, so what can I multiply top and bottom by if I wanted to rationalize? Root of x plus 3. Do you realize you're using the difference of squares factorization process to your advantage, yeah? Okay, what do I get on the top? X minus 9. Okay, on the bottom, should I distribute or should I leave it separate? Separate, why? Yeah, that x minus 9 wants to be canceled out. If you distribute it in, it might not be clear that that cancels out. X minus 9 root x plus 3. Am I missing anything? Yeah, the limit statement. I still have not put in 9 yet. It needs to be there still. The limit as x goes to 9. Now, the minute that dumps away, or it divides out, then you can put in 9. If you put in 9, then what do you get? 1 over root 9 plus 3, which is 6. Okay? Now, question might be, why didn't I write the limit that time? It's because then I was actually putting in 9. So I was doing the limit. I don't write the limit anymore then. I'm putting 9 in finally. That's why it's 1/6. Okay? Last but not least, if you get a common denominator, that's also some algebra. So if I were to get a common denominator in the numerator, what's the common denominator? Is it just x, or is it just x plus h, or is it both? It's both. It's got to be both. They're factors. Okay? So that means this guy would have to be multiplied by x. The next guy would have to be multiplied by x plus h. Algebra error here of algebra 1 and 2 students would be that they wouldn't use parentheses when you should, because you're multiplying this whole thing by x plus h. It must be in parentheses and that negative distributed, otherwise you just lose the derivative. Okay? On the bottom, which is still h. You follow? Follow. All right, so what does the numerator of the numerator come to? Negative h. X over x plus h. Now, let's also do this in a little bit. Do you agree that if I'm dividing that by h, then that means multiply by the reciprocal up in the top, that's 1 over h. So that would then be times 1 over h if I did a little fraction combining. You with me? Yes? Okay, now, at that point, my 0 over 0 problem is going to divide away. What I was getting was 0 over 0, but now it's going to be h's dropping out. And finally, I can put 0 in successfully. If I put 0 in successfully, what do I get? Negative 1 on top, and x times x plus, in place of h, goes 0. So I'm going to get x times x plus 0, which is just x times x, which is x squared. Follow? Are you with me? Okay, cool. You need to also be able to do a limit analytically with a piecewise function. This also is a stumbling block for a few, so let's go over that. When I get a piecewise function, it's one or the other, not both. I should never be giving two answers for any limit. Okay, it's one only. You need to decide which of these two branches I should be using. Look here, if x goes to 1 from the negative side, wouldn't that be less than 1? Yes? Well, if it's less than 1, that's from the negative side is less than 1. So I'm going to use the less than 1 branch. That's this branch, which means then I use the x plus 2 rule. And can I just directly substitute the x value of 1 into that rule? Yeah, what's 1 plus 2? So I get 3. Okay? All right, so the other one, that's one from the positive side, I think that says. Positive side means greater than 1. greater than 1 is this rule. What's x squared minus 1 at x equal 1, or as x gets closer and closer to 1, that would go to 0. Okay? Here's a paying attention check. Therefore, what is the limit? Not from the left, not from the right, just the limit at 1. Does not exist. What must I say? Can I leave it that way? No. Danny, because. Do you want to do this analytically or verbally? Analytically. That means the limit as x up, actually, now, I say evidence, right? Do you agree that I said you have to show the evidence, yeah? Is the evidence already here for the person to see? You could. It is. All right, so if in your previous work the evidence is there, then you can just say because the one-sided limits are not equal, the evidence has been established. You don't have to say it again. I'm not that big of a jerk. Evidence, in terms of notes, evidence already found. Okay? You follow? That's true on the AP test, by the way, as well. If in a free response you established that already, then you don't have to say it again. Although, if you wanted to really cover your twist, you could. Okay? All right. So we've done graphical. We've done analytical. Let's hit numerical. Sometimes you get a limit that looks analytical, yet you get 0. This is okay on your notes as far as I changed the notes after I changed the presentation. Is this in the next column? Okay, cool. Okay, do you agree that when you do that, you get 0 over 0? Yes. Okay. Unfortunately, with absolute value, that's super tricky in that you're canceling stuff out. It doesn't. Those x's, they're built x's, but the absolute value matters. You can't just cancel them and call it 1. It doesn't work that way because absolute value does something. Don't you agree? You can't just blow it off and say, screw it, I want to ignore it. You can't do that. You have to deal with it. There's not really algebra to do. Well, if that's the case, if analytical methods fail you, then you have two things to do. You could graph it, especially if you're familiar with the graph. Most people aren't familiar with that graph, okay? Or if you had your graphing calculator, or you could do numerical. That's what we're going to do here. Now, when I say numerical, I just mean put in a few numbers and see what's going on, all right? In terms of showing good work, your table might look like this. I really want to know, as x gets close to 0, what happens? But again, we have to approach from the left and the right. So you can see that I am approaching 0. I'm getting closer and closer to 0 this way from below. -1 is pretty close. -0.1 is really close. -0.01 is really, really close. This is the preferred way to approach by powers, especially tens. Rather than, I could say -4, -3, -2, -1, and that is approaching, do you agree? But it sometimes won't yield the right answer. This is the better way to approach it, is by getting closer and closer in orders or powers, okay? You can actually do this mentally. If I put a -1 into absolute value, what is it? 1 over -1, because the bottom doesn't have absolute value, so it stays -1. What does that reduce to? -1. What about when I put -0.01? It'll be, top would be positive 0.1 over -0.1, which is again -1. -1. It seems like the negative side is always, the top is getting made positive, the bottom stays negative, but the numbers are the same, so it's always -1. What about on the right-hand side? You can see I'm starting far away, like I might on a graph, and getting closer as I get closer to 0. So that would be more like 1 and 1, okay? So from the left it approaches -1, from the right it approaches +1, and so what's our answer going to be? Does not exist. This limit does not exist because the one, now do I have evidence below? This really does give me my evidence, okay? If you didn't have these arrows, then you probably have to say it, because without saying it, you're really asking the reader to say, hey, figure out what's going on in my table for me. I'm not going to tell you. You have to probably say something like, because the limit as x goes to 0 from the left of What do I call it? What do I put in? I don't really have a name for this, so I'm going to write it. And the limit is, from the left is -1, which is not equal to the limit as x goes to 0 from the right, which is not equal to the limit as x goes to 0 from the right, which is 1. Okay, now again, I know it feels like a run and it's super symbol crazy, but when you understand what you're looking at, it actually makes perfect sense. This limit, which is -1, is not equal to that limit, which is positive. Okay? Now that's what you do. A table is one way to go when direct sub fails. 0 over 0 is not okay. It doesn't mean, it's just so we're clear, this is not DNE because this is 0 over 0. It's DNE because the one-sided limits are different. Understood? Don't think the minute it's 0 over 0, it's DNE. That's not true. Okay. Now, let's talk infinite limits. How many do you want to time here? Whatever, let's just do what we do. Okay. Infinite limits. This also is a huge part of calculus. Really, you could argue, if you were from the background of India or even China, you could argue that calculus was invented there because they started talking about infinitely big and small probably 800 years before, you know, Newton and Leibniz did, but apparently because they're not white, it doesn't count. Whatever. But you can say calculus was invented much earlier. 1 over x, what does the graph look like? Hello? Oh, sorry, you're still getting over my white comment. What does 1 over x look like? Looks this way? And this way. Goodness gracious, is this true? I mean, you know that graph, right? Okay, good deal. All right, wouldn't you agree it has vertical asymptotes, a vertical asymptote and a horizontal asymptote? Yeah? Okay. Let's also get this graph. What does 1 over x squared do? How is it similar? How is it different? Okay, they're both positive. Because of the square, you cannot get a negative y out of this. The top can't be negative. The bottom can't be negative. You can't get a negative y now. So that means if y can't be negative, it must be up here. It still has the kind of the same shape. As x gets big, dividing by a big number gives you a small number. So that means it has to go this way. And dividing by a small number, 1 divided by 1,000,000,000 is 1,000,000,000. It has to get big as x gets small. So it looks that way, and because this function is even, the negatives will behave exactly the same. All right. So you've got some asymptotic behavior there, but it's a little different. Now, let's talk about, the goal is to see how sometimes we get infinity as an answer, or sometimes we get infinity as the question. That's this section. When x goes to 0 here, what is the limit? Okay, infinity. Others? Negative infinity. Okay. You're 2/3 of the way there. Does not exist. Okay, there we go. Does not exist because the limit as x goes to 0 from the left of 1 over x, the limit of something, it's never just the limit with nothing there, it's always the limit of something, is, what's the limit from the left? Negative infinity. And that's not equal to the limit as x goes to 0 from the positive side, which is equal to positive. Okay? How about the one next to it? The limit as x goes to 0, 1 over x squared. Infinity? Is it the same on both sides? It is. Okay? And again, technically, because it's not a number, you could say d. But really, I would prefer you say it's infinite, because that communicates it's infinite, but on both sides, right? Would you put a little note down here? If, as x goes to some number, y goes to infinity, then you're looking at something like this. Think about this, C, okay? If I draw a curve that as I draw closer and closer to C, y starts to get bigger and bigger, what must it be? it must be a vertical asymptote. Okay? All right, let's go back to right above that. The limit says at x at infinity. Now we're going to talk about, rather than x going to a constant, x going to infinity. As x goes to infinity means I just go forever to the right of the graph, right? Well, if I trace along this graph forever to the right, as x gets bigger and bigger, where do the y's approach? 0. Y's approach 0. So the limit is 0. Do I need to approach from above and below? I'll say that this way. Do I need to approach positive infinity from above? That's ridiculous. You can't approach positive infinity from above. It goes on forever. There is nothing better than it, bigger than it. You with me? So that's silly. How about this guy? The limit as x goes to infinity of 1 over x squared. As x goes to infinity, I'm going this way. What if I approach? 0. Okay? Now, here's the deal. Would you also get down a note? If, as x goes to positive or negative infinity, y goes to a constant. See, you see how these are kind of switched? X goes to a constant, y goes to infinity, or x goes to infinity, y goes to a constant. If you think about that graphically, here I go. I'm going to infinity, so x is going to get bigger and bigger. I'm going to draw some kind of curve. What if y went to or approached 0 here, but let's say it approached 1. If y gets closer and closer to 1, then what's going on then? It's a horizontal asymptote. So you need to get into your brain, and this is hard, it'll take time, but you need to get into your brain if one of the variables is going to a constant, the other is going to infinity, that's an asymptote on the graph, okay? Whether it be whether the horizontal or vertical. Okay. I guess I already wrote that over here. Sorry to waste your time. All right. Last but not least, we're doing so great. All right. The Saxon book teaches this in a little different way than I do. The book requires you to do a lot of work, and I don't like that, quite frankly. So I do this in a bit of a shortcut. This is the way you'll eventually get to anyway, and you're smart enough to understand it, so let's just do it the quick way, shall we? Here's the deal. When you have an algebraic limit with x is going to infinity, then there's a method to doing this. Now, really, I have this big, huge, complicated thing, and it feels super complicated. But in essence, it's really a fight, okay? It's a fight between the top and the bottom. If the top gets bigger faster, then the overall outcome will be getting big, and you'll get infinity, yeah? If the bottom gets bigger faster, then the bottoms win. What happens if I get a fraction that's got a way bigger denominator, like 5 over a billion? What's that close to? It's close to 0, right? If I divide 5 into a billion parts, each part is practically nothing, yes? So if the bottom wins, it'll go to 0. If they have kind of equal parts, then it's a bit of a draw, and we figure it out from there, all right? So that's really what's going on in my mind. Which dominates, the top, the bottom, or is it a draw? That's called end behavior. We'll talk about that later. But all you really have to focus on is the biggest powers in the top and bottom. The most powerful term in the numerator, circle it. It's the x squared term. Okay? The negative 6x, it's fine, but it doesn't win. This x squared dominates that term. The bottom, it's the 3x cubed. Make sure you look at the sign in front. Always circle not just the coefficient, but the sign in front. Really, as x goes to infinity, that's all that matters, the biggest and the biggest. So if I look at how those two relate, this, in time, would approach just the same as the limit as x goes to infinity of x squared over 3x cubed. How would that reduce? 1 over 3x, okay? I looked at the most powerful top and the most powerful bottom, and then it reduced, 1 over 3x. Now, in essence, then, the denominator had a little more power. So as x gets huge, the bottom will get bigger faster. What would be 1 divided by billions and billions? It would approach 0. And so the answer is 0. Okay? Doing the same kind of methodology here. If I focus on the biggest, here it's negative 4x cubed. The biggest here, it's x squared. this would behave something like this as x goes to negative infinity this time. What's that reduce, please? Negative 4x over 1. There's more power in the numerator, so there's more x's left over in the numerator. As x gets negatively infinitely large, negative 4 times negative 1 billion, negative 4 times negative 1 trillion, what is that approaching? It's negative 4 times negative large. What's negative 4 times negative large? Positive large, okay? And positive large is infinity. Okay? As x gets bigger and bigger, the top will win, and so you'll get bigger and bigger numbers. Try example 19, please. What do you get? Negative 5. The powers are the same, so it's going to be like negative 5 million over 5 over a million. Negative 5 trillion over a trillion. Negative 5 quadrillion over a quadrillion. It's always going to reduce down to negative 5. Now, we just said as x goes to infinity, y goes to a constant. What does that mean graphically? Horizontal asymptote, beauty. Now they didn't ask, but really what's going on in my mind is, as x goes forever this way, y is approaching negative 5. I don't know exactly, the graph's probably got a whole bunch of mumbo jumbo in there, maybe poles and vertical asymptotes, all that stuff. But I know that the end behavior is that it approaches a horizontal asymptote of negative 5. What about this? Has a horizontal asymptote at 0, or the x-axis, yeah? Okay. Last but not least, find out vertical and horizontal asymptotes of this bad boy. Now, please pay, we'll do this a lot. This is actually one of the big ideas of calculus. 0 over 0 is a hole. You should first remove any common factors. That would be a hole in the graph. Okay. I'll note that there's a hole at x equals 0, but for the rest of the problem, for the question, the vertical and horizontal asymptotes can be found with that removed, and it's much easier to work with that removed. So I'm going to say this is now sort of, not really equivalent to, but I'm going to say x plus 2 squared. Okay. Vertical asymptotes, they happen because you're dividing by 0, because you're trying to divide by something small, 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 and you get big, big, big. Vertical asymptotes, therefore, are if you have a 0 in the denominator. You would get a 0 in the denominator if x is negative 2. And therefore, you have vertical asymptotes, or vertical asymptote at negative 2. Horizontal asymptotes, and I say this over here, is as x goes to infinity, does y approach a constant? That's the question to answer that. That's what we have to do to answer that question. Is there a horizontal asymptote? Well, what happens as x gets large? That means a limit. There's a horizontal asymptote if the limit as x goes to infinity is some kind of constant. This is kind of like we just were doing, except it's not multiplied out. It's fractal. A little easier here. You could either on paper or even just mentally say, what's the dominant term in the top? If I were to expand this out, what's the greatest power you'd see? Negative x squared, okay? In the denominator, x squared. So as x goes to infinitely large, what would that approach? Negative 1, yes? And that implies then that that's what the function, or y, is approaching. Where if y is approaching negative 1, that's a horizontal asymptote. Horizontal asymptote at y equal negative 1. This is a vertical asymptote at. Okay? Remove the hole. Look at the x. Okay. But at any rate, you do not have to turn in that first review today. You haven't got to it. We'll try and get some time Monday. So if you want to turn it in today, great. If you want to keep it to Monday, fine. Your homework. Oh! Ha, good try. Your homework is this. It's 11 questions. It's not too bad. You just have to get in the notes. It'll be fine. Use your notes. Make sure you take your notes on, and this will go great. Unless you take really lousy notes. You should need to take your book home this week, by the way. Should not. You can read it. Hi. Boo, after that. After that. Did you have calculus last year, or were you used to well, then at least for now, I don't have enough yet already, but ask me to read before, and I might have some of it copied off, otherwise it's the website. Okay? Yeah.